we are finally getting to the section where we will do some machine learning, some linear regression first. The next class will be classification. So let's see about machine learning. That's maybe the most fun part, I guess. Machine learning has two main things, supervised and unsupervised. This module will cover the supervised, and unsupervised we'll do it a bit later. There are two main things for the supervised machine learning. Either we have a regression problem, where you are trying to get a numerical answer, some number. In our case, we will just do linear regression, so we'll try to put a line into the data and use it to predict some values. Another thing that we will try is classification problems, where you have a categorical answer. For example, you have an animal and you have to decide if it is a dog or a cat, right? And in there we had some bias algorithm that we had the spam detection that we already did, and there is a decision tree which we will do. You did it already at the very first class as a little preview. There is k-nearest neighbors and some logistic regression. Unsupervised learning, it is machine learning where you are trying to maybe find clusters or do dimension reduction. So we will do it later. With the supervised learning, what we are trying to do is guess the future, right? And we are doing it based on incomplete information. We are missing the thing that we are want to predict, and what we are trying to do is predict the outcome for some particular individual. And the typical thing that you can do is find other individuals that look alike, and if you find many things that look alike, then the outcome of the individual you are trying to guess will probably look like the other ones. Of course, there can be outliers, but yeah. So if you want to figure out how some things will turn out, you look at similar things, see how they turned out, and maybe the thing you are wondering how it's going to go will go like the other things you saw. So that's in a way you have this training data, which is look at other individual, and then you have the one individual that you are trying to predict. Somewhat simple way how you can think of what is supervised machine learning is that you want to create some kind of model, typically mathematical model, some system, such that if you give it input, then it will create useful predictions about the input. Right? You have a bunch of inputs where you know what the output should be, and then you would like to have a model such that if you give it only the input, it can create the output, or something close to the outputs. But there are two main things that come with the machine learning terminology. It's label and feature. So label is the thing that you are trying to predict, right? It's the future thing, that the thing that you do not know, right? What's the price of something, or if it is a dog or a cat, or what kind of animal you see in the picture. That's what is the label. We will use it as a Y in the linear regression. Then there are features. Features are the input variables. The feature is the thing that you observe, the thing that you know. So, in other words, I will tell you X, and you are trying to tell me what Y is. Here, the label that we are predicting typically is just one thing. You want to predict one number or one category. And the features, you can have many. So the X is not maybe one real number, but it can be a bunch of numbers. Right? The more you have, the better chance you have of creating a model that works well. Here's an example, our iris data set. Here we have the data, you have the sepal length, width, petal length, width, and species. question is, what are the features and what are the labels? Well, if I just ask this, what are features and what is the label, it is not a well-posed question. The thing what is feature and what is label depends on what are you trying to predict. Okay? If you are trying to predict what is the species, then species is the label and lengths and widths are the features. If you would try to predict sepal length, then sepal length would be the label, and the sepal width, petal length, petal width, and species would be the features. Right? So the definition of feature and label depends on what is the thing you want to predict, that's the label, and what are the things that you know, that's the features. Right? Typically, if you are having some data set, you pick one column to be the label and the rest to be the features. Linear regression is a model that will predict a numerical label. So a label is a number, you want to predict a number, and the features that it can use must be also numbers. Right? So it is a map from several numbers to a number. Models will first try to do linear regression. This is one of the inspirations what you may have as a question for your final project. For linear regression, we will use the library scikit-learn. If you are using Python in some offline thing on your computer, you may need to install it. Scikit pip install a scalar. Right. We will try to predict price of diamonds based on the features. We will be using data set that is available on Kaggle. And so how does this thing work? We import pandas, import Seaborn for pictures, and then from a scalar import linear model. Creating runtime, and if you are opening this in the Google Colab, this will just work. No need to install anything. Right. Our question here is the following problem. You are trying to buy a diamond. Imagine that. Right? I do not know why would you want to do that. If you saw any show of Adam Ruins Everything, but let's assume that you are buying a diamond. And I have one that I would like to sell. It has different features here. It has 0.35 carats, cut ideas, clarity, right? Depth table, everything you may want to know about it. I'm offering the diamond to you for $2,000. Question: are you buying it? Right? Are you buying the diamond or not? Right? You would like to make this data-driven decision. It's a great buzzword, right? And you can do it by looking at prices of other diamonds and I see. And based on that, you will be able to tell if the price is fair or not. Right? We will work on this fun exercise or example. There is a data set about diamonds, right? And the diamonds have carats, cut, color, clarity, depth table, price, XYZ, whatever those features are. And what we would like to see is a price. Right? You come to a store and you want to buy a diamond. I have a diamond for you that I would like to sell you, and you can look how the diamond looks like. You can observe it, and the question is how much do you want to pay for it? What's the fair price? Right? how do you figure out what's the fair price? You look at prices of other diamonds, try to figure out what are the costs of the other diamonds, how are the features of the other diamonds, and then you can decide if the price is fair or not. Right? So here is what are the features and what is the label. I want to predict the price. Alright, the price is the thing that I'm interested to know. So price will be the label, and everything else will be the feature. Data that contains lot of diamonds. You can make a better decision about the price of the diamond I'm trying to sell you. df.head, let's look. Now the data here have everything that I told you about my diamond, but also it has price that I didn't tell you for my diamond. How many things we have? There are almost 54,000 entries. That's good. It's a lot of data. This is the data of my diamond that I'm trying to sell you. So let's see. I will look at df.describe. And I have to comment out the other two. Okay, so it will tell me for each, now these are the numerical values, what are the minimum, maximum. So the carat, I have 0.35, and 0.35 is between the minimum and maximum, which is good. Depth is also between the minimum, maximum. Tables between minimum, maximum. Price, maybe the one I was guessing is between the minimum, maximum, x, y, z, kind of, right? So what I am trying to do is see if the data I have about the diamonds somewhat contain the diamond parameters that I am trying to predict. Right? If here we have the carats go from 0.2 to 5, if I try to sell you a diamond that has 10 carats, well, then the data you have will probably not be good for giving you a good estimate how much such thing should cost. Right? Suddenly maybe there is some rarity thing and it will be way more expensive than the linear model would expect. Right? Who knows? So I'm trying to say it's good idea to look if the data that you have in the convex combination somehow, the data you are trying to predict. If you use linear regression, how do we calculate the price? So if you look at the numerical features are those columns that have some number to it, like carat, depth, table, x, y, z. And I guess the first column, that is the index, we shouldn't use, and we cannot use right away the cut color and clarity because those are not numbers. Right? And then we will try to say that the price of the diamond is a linear combination of these features: carat, depth, table, x, y, z. And I will combine them together with some real numbers. So the A, B, C, D, E, F, G, if you look at the equation, will be some real numbers. I am trying to say that the price depends on the carat, depth, table, x, y, z, and maybe there is some offset G. So question is, can you find this A, B, C, D, E, F, G, or what's the best way to find these real numbers? We are trying to write it as a linear combination in a way. A little more abstract way is the following. I have x, which are features, y that is label, W weights, and I index of the data. So every row in the data that we have corresponds to one diamond that we saw, and the diamond has the features, and if I fix the W, the weights, I would like to say that the price, here I will write it as yi, that's the thing I am trying to predict, and I means that I have the entry index I or ith row, right? And it will be the features x1 i1, xi2, xi3, xi6. I have 6 of these features, and I will combine them with the weights w1, w2, w up to w6. And then there is the variable ei, right? If you look at the way how I wrote price equals this linear combination of character table, it doesn't have any ei in it, right? That's what I would like to happen, but maybe it is not really linear. We are also forgetting some of the features. So the price that I know what the price is will be the linear combination of the xi's, and there will be the ei. Ei is like the error, how much of the prediction is, right? So on the right, if you choose what the weights are, the given weights will give you a guess of a price, right? And the ei will be how much of it is compared to the actual price, yi, right? So yi is the actual price, and on the right you have the price that you guess, and ei is the error. You can think of it that the w0, w1, xi1, blah blah blah, all of these will make a line. So you have the picture on the right where you have the line, right? And in the line, if I would say x equals 1, then I get the blue point on the line. That's the term w0 up to w6 xi6. But the actual value, the yi, is the red dot that is at 6, right? And the green line is the error. How off is the line, the prediction, the thing that we would think what our model is giving us as the price from the actual price. Right? And I would like to have a model such that these green lines, the errors, are small. If they are small, life is good. You have a good model. If the green errors are big, then maybe the model is not right. How do you figure out good model? What is the good things? You would like to minimize the EIs, right? You would like the errors to be small, right? You can notice in the picture on the right that some of the lines are going up and some of the green lines are going down, right? So sometimes the error is positive and sometimes the error is negative. So if you just sum the errors, maybe the positive and negative will cancel each other. Perhaps it would be good to sum absolute values. If you sum absolute values, you always have the errors added up. The trouble with absolute values is that it doesn't have derivatives, so some of the numerical methods don't like absolute values. So instead of absolute values, you can use square. So we square the errors. Now if you square the error is greater or equal than 0, and you sum these errors up for all the entries that you know. So for all the diamonds that you know, you sum up the errors squared, and you are trying to minimize this, right? And what is the thing that you have a freedom of? You have freedom of choosing the W. So you try to minimize the sum of the errors squared over all possible choices of W. Right? The square error also has this feature that if you have some points that are off a lot, then you get a bigger penalty. If you are off just by a little bit, the penalty is not as big. Okay? one could write it a little bit more in a matrix algebra version, that you say x is a big matrix, y is a vector, w is a vector. So matrix is you can think of it as a two-dimensional place where you put entries. Well, you could think of it as a data frame, like it has two coordinates. Y is a vector, w is a vector, I is index of entries. The yi is still the same, but now the least squares errors, you can write it as w times x, or x times w, which is the left on the right part, the left thing. Then minus y, which is now you are subtracting y, which will tell you what the error is, right? Or maybe you are calculating the minus e, but it doesn't matter. And then you can take this and square it. There is also square root in this norm, but doesn't matter that much. And this thing is something that can be solved using gradient descent method. If you take calculus 1, you may hear a little bit about gradient descent method. What it does is it starts with some w, and then tries to see if changing the w a little bit will improve the minimum or will decrease the value of the objective function, and it can slowly move towards the minimum. Good news for us, we will not have to do it ourselves. The library that we will use will do all this for us. It's important that we know what the library is doing, because then we may have a better idea why the model may work well or why the model may suffer. So this is the possible implementation, how to do the linear regression. You have to prepare x, you have to prepare y. So I have a x as a two-dimensional array, y as a long vector. Then you create an instance of linear regression, and when you have it, you just write regr.fit x and y, and by calling this fit x and y, you will get the minimum w's that we had on the previous slides. So all the gradient descent and fitting the thing is done here is with one command. And then if you want to use the model and see it for prediction of unknown, you call function predict. Model, create a model and make a prediction. Right. So we usually have x as the features, y as the label. This thing we want to predict. We want only numerical values. We will only use the numerical values for x. We will ignore the one that have category. Alright. So first I will prepare the x. Okay? I have my data frame df, and I will take from the df only some things. So if I make something like this, I select only some of the columns. Right. So let's see what columns do I need. I need carat, depth, table, price, xy, and z. Right, let's see. Incomplete input, one more of these. Right, so now I have the x. Okay, maybe this is not the x. I do not want the price in, right? Price is y. Take the price away. So these are the features. This I will call x. Pen. Right. Now I will do the series for y. Right? Here are the prices. Y equals df price. Okay. You can always try to write print x dot head. Check how the head looks like, how the big oops should make some zooming here, and how the y looks like. Right. Okay. Good. So now we'll make the model. Okay. I have here how we should do it. So there you go. This is now object that will be holding the linear regression. Linear model dot linear regression. All right. Nobody is complaining, so we have the model. Now we can fit it with data. Fit x, y. Ta-da! And now this object Regression has inside the solution for the linear regression. Okay. And now if I want to use it, I can do predict. Right. Okay. We do it this Regression predict, and here I have to put in the x. So here is the carat from the diamond that I am looking at, 35, depth 61. This is not helpful right now. 0.5, table 55, x is 4, y is 4, and z is 2.5. Right, so I will call predict like this. Right, I put in the data. Now this doesn't work because what the predict does, it is built to predict many things at the same time, not just one at a time. So you want to write it as a list. You have list of lists, and then it will work fine, right? And it returns array that is saying 1, 5, 6, 7. So the linear regression suggests that the price of the diamond, based on the diamonds that you put in, would be expected to be $1,567. So if I am trying to offer it to you for 2,000, do you wanna buy it or not? Right? Maybe you don't want to. Here is a warning. Warning: X does not have valid feature names, but linear regression was fitted with feature names. So what happens is that when you are creating the linear regression, X had the names carat, depth, table, but when I put in these numbers, I didn't have the names for it. So what you could do is you can have here values, and then it's fitted without the column names, and now it's not complaining anymore. Right? So maybe I'll write here comment can call fit x, y, but then predict complaints about feature names. Okay. So if you want to have more diamonds or different diamonds, you can try to predict more things. Right? So it's very simple model, the regression. Let's see how it actually looks. Right? There should be some linear coefficients, and we should be able to extract from it how the mass looks like. So Regression coef. Here we get the coefficients, the linear coefficients. If you write x columns, this is what they correspond to. each coefficient corresponds to one column, and then there is this intercept. It's the constant that you are adding in. Alright, maybe I will try to write it out a little nicer, right? So we know what this is. What you can do is you can do a for loop predictor coefficient. Maybe you can write this as a feature coefficient. And now I will put two columns together, and here is the names. Put the names there, and then I put the coefficients. So it will go through the lists, columns, and coefficients, and it will take the first entry from both lists, and from the first one it will go to predictor, the second one to coefficient, and so on. And now I'll print them out. Predictor, coefficient. Alright, let's see, what did I mess up? Predictor not defined. Alright. Carat depth. Okay. And print intercept. Alright. I will now have a little bit nicer write-up. And from this you can try to figure out what is the linear combination, right? So I will try to write this. Guess or estimate for price. Price is, and here it is. First we add the intercept, so it's 20,000 plus, and now 10,000 times the number of carats minus 2203 depth minus 102 table minus 1315 times x x minus plus 66 times y plus 40 or maybe 41 times z. I just truncated the numbers. So this is a estimate of how the linear thing looks like, which is kind of weird, right? You can think of it, what if I give you a diamond that has nothing, empty diamond, right? You would say that nothing, it has carat 0, depth 0, table 0, x 0, everything is 0, you should pay 20,000 for it, right? And the number of carats, it goes up really high, and then you are correcting it with the depth and x, which have a negative coefficient, right? It's a, yeah, that's what it does. Well, one could think that this is maybe unexpected. Let's look at the correlation. So I will write here the data frame. From the data frame I will do carats, depth, table, what else is there? Doesn't matter in which order we do it. X, Y, Z, and also okay. And what I need is also add here the price. So I'm most interested of the correlation of price with everything else. And here a price has high correlation with carats. So that kind of makes sense that the coefficient next to carats is high, right? Because it should influence the price a lot. The depth is very low correlation, so I am not surprised that this coefficient is small, or the table X has a relatively larger coefficient and has high correlation, but there is a very small for Y and Z, which maybe is a little bit surprising that Y and Z do not have a higher coefficient. But maybe Y and Z are also highly correlated to X, so they don't add as much new values. That's just like a guess, right? I am trying to see if the numbers that are here make at least a little bit sense for numbers that are here. If there was a coefficient that is very high and the correlation was very low, it would be suspicious. Right? This way it's at least not suspicious. Sometimes the correlation is good to see, sometimes maybe per plot is also good to see. So I will take all this data frame and try to do a per plot for it. Maybe code SNS per plot. And there it is. I will change it a little bit and put price last, because I want to see the price last. Oh, yeah, here is the thing I was saying, that you can now see that the X, Y, and Z are very closely correlated. So if you use X, then adding Y and Z maybe doesn't give you as much new information. Right? Alright. So, running this and see how it will go. I put the price last because here the labels are on the left and on top, and if I want to see the first row and see all the labels, it will be great to have it in the first row. In the Seaborn, the labels are on the bottom and right, so now if I look at the price and other things, I would like to see it like this, right? So the price, one could think, yeah, as the carats are increasing, price is increasing. That, I don't know, it looks almost like a line this way, table, yeah. X is good, right? It maybe increases as the price increases, but Y and Z, it's just a vertical line. So maybe this provides a better explanation why there is some higher coefficient for the carats and for the X, but for the Y and Z and these two not so much. Right? What we haven't done, and it's important for you to keep in mind, we created the model and tried to get some number out. We didn't check whether the model is sensible in any way. Right? We called some functions and it gave us some number, but we need to test if the model is reasonable. We will learn that later. We also haven't used any of the categorical data. Right? So perhaps the model is not that great if it is not using other features of the diamond. But it's possible to change the categorical data into numerical ones, and then you can use them as well. So it's a thing that one can try. Right, we'll do a little bit demonstration how to deal with non-numerical data or with categorical data. Right? We had several of them in the diamonds, so we'll give it a try. So we wanted to predict the cost of one diamond. So first thing one could try is to restrict the data you are using. You can say, I only have this diamond features, so I will only train my linear regression on the diamonds that have the same features in the categorical data. Right? That's one option. Another option is that the categorical data sometimes have some ordering to them, right? And if you are lucky, it may be linear ordering. So what we could try to do is map the categorical data into integers. So maybe the cuts, color and clarity, all of them have ordering, which of them are better and which of them are worse. And maybe that will help do something. Or then there is this dummy indicator variables or one-hot encoding. We will do that more carefully later again. The idea is that if you have several possible options for a category, so category has several options, maybe the color could be red, green and blue, then instead of having one column that you have column, let's say, called color and options red, green, blue, you will have a column color red, and everybody will have 0 or 1 indicator variable. Then you will have another column color green, and everybody will have 0, 1 indicator variable. And then there will be another another column color blue, and everybody would have 1, 0 variable. Like this way you can map between the color of red, green and blue to the columns color red, color green, color blue. Sometimes it's better to have only 2 instead of 3 of these, so have 1 less, because if I tell you that the color is not red and it is also not green, then you will already know the color is blue. So by keeping all 3, you are introducing some dependency in the data. But maybe we don't have to worry about it right now, we'll worry about it later. To deal with the data, the features that are not numerical, is that we will try to restrict the data only to those that are numerical, and the numerical that are matching the non-numerical that we have. So we will only want to see data that have the cut ideal, color E, and clarity VS1. Right? So how do we do it? So I have this df cut. I have a cut, blah blah blah, and I would like the cut to be ideal. I have the true false thingy, and I can say I would like the data frame. Right, good. So now I managed to do a data frame where all the cuts are ideal, nothing else. Right? Right. Now I do the same with color and clarity. So I have this. Now to make it, I have to use AND. I have data frame color, and color is E. Yeah, color is E. Right, cut idea, color E. Now I have to check the clarity, and we are done. df clarity equals VS1. Did we mess up? Series is not callable. Yeah, you have to the end. Right. So now the data that I kept on the non-numerical features agree with the features of the diamond that I have. Right. I'll call it data frame A, whatever. So we don't have to look at it. Right. So now let's see DFA shape. I have 600, almost 600 diamonds, right? So this is to see how many records there are. If I would be left with like 5 right? It would be hard to do any meaningful prediction out of it. Right. I will double check. How does the head look like? All right. Right. Good. So I have my data frame. Now I can try to get the x and y. X. I will take my data frame and only take the numerical values like we did before. Carat, clarity, oh no, depth, and table, and I will skip price because that is the y value, and I have x, oops, hopefully, and y, a price. Right, and we do the linear regression. I will create the model linear model dot linear regression. Probably some typos here. Linear model. All right, and I fit it. Fit x. I want the values, so we are it's not complaining. Y. We have the model, and we try to predict the price of the diamond I'm trying to sell you. Look at that, 3,871. So, how about 2,000 price? Are you buying it for 2,000? If over here, this model that now takes into account the features that are not numerical is saying that the diamond would be worth like close to $4,000, maybe now $2,000 looks like a bargain price. Yeah. Let's look how the linear regression looks like. I will trace this. What are the coefficients of the linear regression? This is what was there before. I will try to look at the current one. So I'll do the for predictor predict I cannot spell today. Predictor coefficient in zip the data, zip x dot columns and regression dot coef. I will print predictor predictor coefficient. Something's not right, we'll find out. Oh no, it works fine, it's just complaining. Alright, and I will also write here the intercept, print intercept not intercept. Alright, so now I can try to see how is the price constructed now. Now the price is constructed as intercept, which is the 4,033 plus 28,000 times the carat, and depth is plus 302. How about table minus 54? Maybe if I make it like this it will fit, or maybe not. X is 143. x plus 889 times y minus, oh wow, that's a lot, 11,983 times z. So maybe now it looks more reasonable that you have the intercept slightly lower, you have a lot of weight in the carat, some in the depth, that this is looking a little bit suspicious. But anyway, that's how it is coming out. Right. We can try to do the correlation. So let's see, I will take this, and I will try to include the price. Let's see. String literal, alright, here's sync. Okay. So high correlation with carat still, the big coefficient here that does a lot. Depth not much, table not much, so these are small. X kind of big, but the number is not doing anything. Y is much smaller, but the coefficient is higher, which is interesting. Z has a high correlation, but the coefficient in absolute value is very high. Right. So at least a little bit reasonable. And let's try to do a pair plot. And I will copy this in the pair plot. And I will put the price at the end, so we can see it better on the screen. Okay, I will have a little break until this runs. Alright, here it is. I'll look down here. So here's the price. Here's how it was the relation between carat and price. Nice, one could see that as carat goes up, the price goes up. Depth is random noise table, not as nice. X, it is very nice. Y, it's harder to have a good guess. And Z also looks, well, here's one that's kind of off. Maybe some outlier ruins the day a little bit. Or maybe it would be good to remove this outlier. And another thing that you can notice is this: we are trying to fit a linear function into the data. That this looks more like some kind of quadratic function or some polynomial. So maybe the linear function is not the best to approximate this data. Right? If I have a line that tries to predict price from x, then here the x is bigger than the line now would be smaller, right? So maybe the linear regression is not perfect for this project, right? It works, it does some numbers, but this kind of highlights that there may be some better models than the linear regression. We can also try is look at the possible values of cut, color and clarity, and maybe there is some linear ordering on them, and then put some change them into numerical values. So yeah, I will look at the F. Let's start with cut. There are different cuts. Well, if you try to write unique, it tells you what are all the possible cuts. Okay, print, sorry, it stays there, I don't lose it. The same thing we can do for clarity and color. Clarity different clarities and different color. Right. Well, I do not know what this which of them is better, which of them is worse. So one has to do some best is to do a little bit of search and figure out which of them are better and which of them are worse. What's the ordering on them? So let's assume I did it, and I will try to use some ordering. Right? What is a thing to notice is that if you want to translate the strings into numbers, we will use a map. Right? We had the map a while back, so I will use cut map. Now it is a dictionary, and the dictionary always says what is translated to what. Ideal is well, I guess I can do it like this to make my map a little better. Ideal should be the best one. 5, premium, 4, good, 3. Oh, maybe very good is better than good, right? Very good, 3, good, 2, fair, 1. Right. So, and now we have a map that will translate the strings into numbers. Right? I will create a new data frame map. I will not destroy the data frame that I already have. Right? I have a data frame df map, and I will do the following. Data frame, take the cut. Right? Here are all the cuts, and I will write map and cut map. And now it's all changed into integer values. Right? Df map cut equals stack. Alright, and now if I look at df map dot head, cut is a number. Right? I have to remember what was the mapping, otherwise I will never be able to interpret the results. But at least okay, I have the numbers. Right? And now do the same for the other. So what is it? Clarity map. I will copy these guys over there. And alright, I1 is the 1, SI2 is 2, SI1 is 3. Do not ask me what this actually means. Right? I'm not a person who knows anything about the diamonds. I'm just trying to figure out this one little one. Right? So this is the domain knowledge that you sometimes need to have. Right? Without this, without domain knowledge, I would have no chance. Right? Maybe Wikipedia would help. Alright, clarity map, something's wrong, commas missing. Right, everybody's happy. And color map. Colors. Alright, so D, bad color, D, E, D1, E2, F3, F3, G4. Maybe if I would just write it right away instead of trying to do this, it would have been faster. I6 J7. Right, now I have the map for color. I will apply it in the same way as I did this thing. I have color map, and clarity. Alright, now I didn't mess it up too much. Color, clarity, cut, everything is numerical value, so now it will be great for the linear regression. We can put all of them in. Alright, I will maybe comment this set and have to prepare the data x df map and have to not mess it up. What is the ordering here? Okay. There is more parentheses, carat, depth. I will put those new ones at the end. Table x, y, z, cut, clarity, and color. I prepared x. This is x. Good. Y, df map, price. Right. I have my data now. I'll make the regression. Okay. Make a variable that is an object that has the linear regression in it. Right? Okay, I think I did it well. Now I fit the data x values and y. Bam, it's fitted, and now I can try to predict. Right. If I try to call it like this, it will not work because I don't have the cut, clarity, and color. Right. So I have to put there the cut, and I will say cut is ideal. What I'm trying to do is taking the value that I have, ideal, and I have to map it with the dictionary for mapping the cut first. Then I have to put there the what was it? Next was clarity map of VS1, and finally color map of color E. Alright. Okay, so we got $1,800 as the predicted price of the diamond I'm trying to sell to you. So, is it worth buying? Are you buying it for $1,800? Right. It's wild. We got different estimates based on the models. Right. We can try to do the correlation again. So df map, and here I will copy all this and put the price there first. Dot core, and let's see. Carat still high correlation. Well, we didn't do anything with this. Maybe I wanted to see with the cut, clarity, and color. The correlation is not very high for the price, so maybe it's not as interesting to look at it for the price, right? Well, but we should still see how the coefficients look like for getting the for the linear combination. So for predictor and coefficient in zip, I'll put the two columns together, columns and reg coef print predictor and coefficient, right? So I'm going over the pairs of the column coefficient. Oh, and I messed it up. I forgot column. All right. Carat still high. So somewhat smaller. Clarity surprisingly high, but okay. Doesn't look completely unreasonable because the carat had the high correlation. Maybe high coefficient is good. Set reg dot intercept. Yeah. Okay. This is what we had before. That it was now intercept is 5,000. Carat is back to what it used to be, 10,000, and then there is some massage with the other numbers. It looks like there is nothing that is huge like here, the Z. Right? You can also try to get the pair plot. I will copy this thing. SMS. I'm curious how the price looks. I'll delete it from the front. Okay, now missing parentheses at the end. So I would like to know if the price with cut, color and clarity does anything useful. How do you think it looks? It will be kind of weird because these are integers and only a few different options. So we'll see. Okay, maybe the plot is big, but it's unfortunate thing about Seaborn. It sometimes takes a long time. So, well, it's hard to see the data here. Cut is mostly one anyway, clarity is mostly one, color looks like it's all over, almost, yeah, I can't really read it, right? So it's hard to say. We will try to use this function get dummies. Well, let's see what it does. Maybe it's best to first see what it does. So I call get dummies on the data frame df and list of columns cut. I will add the other categorical columns later. Right? Just first see what it does. So it keeps the data frame, and then for the cuts, instead of having column cut, they removed it. It creates cut fair, cut good, cut ideal, cut premium, cut very good. Right? So suddenly you have more columns, and the columns correspond to the possible values of cuts, and each possible value of cat is represented as a series that is just true false, right? So if in the first one the cat was ideal, there is true or 1 at the column ideal and false everywhere else. So you have this most 1 true per cat, right? So what were the cuts before? Ideal, premium, very good, good and fair. Sometimes people don't like this as much because now you have maybe a little bit more information that you need, right? One of the one of the columns is dependent on the other ones. You could say that if all of them are false, it means that the cut was fair. So now we have a little bit maybe more information than we needed, and not all models are happy with that, but we will not worry about it for now. Alright, so now we try to add the other categorical data in it. So we'll put there the color and clarity. Bam. So all the categorical data are now here on the right, and they are columns of true, false, true, false, true, false, true, false, true, false. Right. Now the table is very big, but everything in a way is a numerical thing. So we can put everything into the linear regression. And why we do it this way and not with the map to numbers like we did before. The disadvantage for mapping it to the numbers is that the relation may be highly nonlinear, right? So let's go with this. Alright. Let's see the data frame dummies. That is this, and there are so many columns that it would be kind of annoying to enumerate them all to get X. So I will just say X is the DFD, and I will drop price. Maybe I will first try to do it without it. Price and X is 1. Alright. Okay, good. Price is gone. I should perhaps also drop the very first thing. So the fd dot columns 0 is the unnamed. I don't think that index is a great thing to include in the predictor. Alright. Now we have a Kana depth table. Okay, good. This looks now much better. Right, so this is the X. I will create Y, DFD, price. Right, now I have X and Y, and life is great. Right? I can print X dot columns just to make sure. This is all the columns there are. So much, yeah. Alright, so we'll take the model, linear model dot linear regression. Bam. I will fit it with the data that I have. Regression fit X dot values Y. I'm not doing anything, I'm just checking that I'm writing it in well. Alright, and now comes the tricky part, and that is how to create the data for testing. Right? We had this as our diamond, and now this is the order of the columns in X. So what you can do is to create, you have to expand the cut, color and clarity, right? So 0.35, 61, table, and now the cut was the order of cut. First is fair, it is this one, good, ideal, we had ideal cut, right? About and then there were two more cuts. Now color DE, so here color E is true, this is color E. And finally the clarity BS1, 1, 2, 3, 4, 1, 2, 3, 4. Okay, good. So now I have the input data. I have to work on it a little bit to make it work. So now I do regression.predict and call it this test. Is the only one thing I'm looking at, and it is saying that I should be paying minus $50. I think that something got messed up, or maybe not. Maybe this is what we should be paying. Let's see again. First is carat, then there is depth, then there is table, then there is X, then there is Y, then there is Z, and then there is the cut. Well, yeah, the diamond I'm trying to sell you may be completely worthless. So this is a danger of predictions, right? It may be, yeah, I'm sure it is not worthless, that I shouldn't be paying you $50 to take it off my hands, right? Here is the coefficients of the linear combination, carat, high value, depth table. X has big negative, little bit like we had before, and then I would think that these are kind of high numbers for the penalty or additions. So anyway, this is how the linear combination looks now. All right. So do you want to buy the diamond or not? Are you buying the diamond? Well, which of the predictions do you trust? Right? We tried several different predictions, and the value of the diamond varied wildly. Right? Which of them do you think is the right one? Right? We haven't done any of this. So one should create some validation for the models where you do some train test split or cross validation. We will do those later. It will let you see how much you should trust the models, right? Sometimes the models are very good, but sometimes the data just are not good for the model you are trying to use. So maybe in our case, the model we tried to fit in was linear, but maybe the data are not linear. Right? We just looked at this little pair plot, and the pair plot showed that maybe the data didn't have quite linear dependence for the price, and then yeah, you may get weird results like that. I should pay you to $50 to take my diamond, right? So something one has to check carefully, do some visualization of high dimensional data we haven't done. We will do that as well, right? So this was just a quick demonstration so for you to see how one can create a model and train it, and then make the model predict something. Right? So this was just the first glimpse of what you will eventually be doing in your projects, final projects. If you are eager to try things on your own, there is a competition of predicting prices of houses in Ames, Iowa. Right? So here you can look on Kaggle, and there is a lot of data about houses in Ames, and you can try to figure out if you can guess what is the price of a house. And if you want to learn more about linear regression, I again recommend StatQuest. It has very nice simple explanations about how linear regression